Why, hello there. I noticed more than one person actually viewed the last video, so maybe I'll continue with this. Let's see what I've got here. I added to my graphics objects another object called a graph, a graphics object, which draws a graph. Given some points. Now, as far as scales and so on, I'm just going to work with pixels. It's easy enough, easy to understand. Now, obviously, it has two lines in it. Now, it can have an array. One way to do it is for it to have an array of what I've called B points. So they're like points, but that use floating point numbers rather than integers, because that usually graphs that you deal with, although in the end it's going to be an integer that you plot. You start out with floating point value. No, most of the difficulty was in just drawing the graph, and then I decided to give it a function to display, and here's the function I gave for it to display. I added points going everything is a rect, if you recall, so it has a width. If I go from minus half the width plus a little bit, so we don't go to bounds, to 0 plus half width minus a little bit, and break that up into 200 intervals evenly. So starting from the left, adding each time adding 1/200th of this difference, which actually isn't exactly this. No, that is right. Okay, it's this difference, not the actual width. Then what I'm drawing here is a sine function. The thing itself, it's this one. Its dimensions are given in the constructor. I guess I should have not done it that way, but whatever. 400 by, oh no, sorry. This is the origin of the graph, and this is the width and height. Now, so that means it's centered with positive and negative, which isn't so great, but it can all be fixed up later. Just wanted to see something go. But that's perfectly fine for this sine function. It's the sine, this particular function is just some complicated mess, trying not to go to bounds, a little bit less than height, times sine, which goes from -1 to 1. Now, I found it looked a bit too silly going all the way to the top and bottom, so I divided it height by 4, and I'll just run it, show you the graph. Here's my graph, sine x. And so the difficulty was adding in these little tick marks. I suppose I could put a 25 here. I couldn't fit two 25s this spot. This one will have to act for load. But anyway, so there's a sine x. No, actually, it's not the usual sine x. I'm off by a half cycle, I guess. It should be. This is not the 0 point, like the argument equals 0. Doesn't matter. It's a graph, and it draws on a thing here. Now the way that works. Now there's this B in motion. I'll get to that in a minute. Draw the axes. I make a thin pen for drawing these numbers because the regular font is just too thick. They get in the way. But if I add a little shadow to these, they're visible, but they're not in the way too much. And then select that font into the device. And here I'm drawing the ticks. That includes the ticks and the numbers. And this is my computation for doing that. It's one of those things that you just work it out. Then if it's not in motion, one thing I can do with that little graph is make it move. I'll do that in a minute. If it's just a static graph of points, I just go through this is an array, the array of points, and plot a pixel. There's really nothing to it, as long as they're within the rect of the graph object, they can be drawn. And there you go. There really was nothing to doing that. The graphs that I'm going to be more concerned with, as far as the interpolation and stuff, won't contain as many points as this. Not a lot of interpolating is required in this case to draw a smooth curve. It's already looking like a smooth curve without any adjustments or anything. But anyway, just to have a look. Now, another way one can do this sort of thing is instead of having an array of points, although in the end I want an array of points because the discussion is going to be on interpolation. And that's when you have a whole bunch of points and you don't know what the function looks like, but you want to make a guess at as to what it might look like. So our data will be some points, just a few points. But another way one can do a function, a graph like this, is instead of using an array, you could have a function, an actual function that you call, given some x, it would return y. Now I called this function a wave function because this in fact is not because it's a sine wave. This is a wave function for the basic reason that it's a solution to the wave equation. If you don't know what the wave equation is, I actually wrote it out and emailed it to myself using that Gmail text. Here it is. This is the standard one-dimensional wave equation. That's a 2 there. Can't read it. It's a partial differential equation. This says that the second partial derivative of function u with respect to x, if it's a two-variable function, as x and t as its variables, independent variables. If you differentiate with respect to x twice, then that's the same. I should have put v equals 1, but whatever. Then that's amounts to the same as differentiating twice with respect to t. Now it turns out that any function of this form is a solution to that equation. It's very easy to prove. What I mean by this form is that this here, f, is a function like a x squared plus 7 type regular old function, and x and t always occur in this combination. So if it was x cubed plus y squared, plus x squared plus x, it would be this cubed plus this squared plus this, you know what I mean. The partial derivative of such a function with respect to x is the same as taking a regular derivative of this function, its form, as if this were a single variable, and you would get a minus sign from the chain rule, and doing it again you would get a double prime derivative of this f, whatever it is. You can have any form as long as it's differentiable 2 times. And if you do that same thing with t, the same thing happens, except you get this. Each time you do it, you get a v, an extra v comes out from the chain rule. So it is clear that maybe I got it backwards. This should be 1 over v squared. Yeah. So I do have it backwards. This should be that the real answer is x. U, whatever function. Second derivative with respect to x is one over v squared there. That works out correct, because I have to divide this thing by v squared in order to get this expression. So whatever. That though tells you that if you ever see a partial differential equation like this, you know immediately that this function represents something that moves. Now, it's how do I explain that? Why that's true? If t represents time, okay, and x distance, and if we allow for the fact, the idea that time is an ever-increasing quantity, all right, then in order to then as time elapses, this argument would increase, right? Well, it would increase, and we would see this thing changing, unless we moved along in the positive direction, right? At a speed v units of distance per unit time. That is the speed of this thing. Let me get out of here. In order to, if we wanted this thing to not change as we're looking at it, this would have to be true, right? Clearly, if these two things are equal, then the form of this function remains the same, right? Now that's the same as saying that v is the velocity with which this function moves in space. We can say that v here is x divided by t, which is the standard definition of velocity, distance per unit time, right? Now looking back at this thing, this function, no matter how complicated it may look, is a function of x minus something times t, so therefore it's a solution of the wave equation, and therefore it would move if t were allowed to advance forward. So that's what I've done here. If I press the letter G, this flag will change and my tick count will reset. And every once in a while, I will be asked to redraw myself, and I'll pass into the wave function the amount of elapsed time and some constant, which happens to be velocity, and my current position x for at each point along in the graph. And so that'll give me a plot of what the graph looks like at any given time if this value has a non-zero, comes up to something non-zero, that this will change. Well, I'll just press G, and there it goes. So now that's a thing that moves, and it's called a wave function, not because of the fact that it happens to be an oscillating shape, but because it's a solution to the wave equation. Because solutions to the wave equation don't have to look like sine waves. They look like any shape, any function that satisfies that requirement, that it's only that the expression, whatever it is, can be written in terms of combinations of this, and this only will move and will be a solution to that equation. Just a little bit of trivia for you. So next thing I want to tell you about is these Hermite curves. I'll get to that next time. And the Hermite curves are so important that really everyone should know about them, and it's really not very complicated at all once you look at it. And like I said, somebody gave a very good explanation, and I will go over that explanation of how they work next time. And you should see immediately how it works. And from there, one can derive special cases of the Hermite curves, called some of the splines, something called a Cardinal Spline or Catmull spline, and all these various things that are used in computer graphics and games and whatnot, in motion simulations and all sorts of things. Okay, so you know this part is working. I can make a graph, and I just have to. I'd like to be able to demonstrate not just with those pictures, but physically on here the principle of those curves. It's very simple, but seeing makes it even easier. Really seeing something happen, I think, makes it easier to understand. Okay, well, hope to see you then.